Hello everyone. So welcome to a new lecture on the topic envelope detection and smoothing. This is the course on signal processing algorithms and architectures. I am Dr. Anirban Dasgupta and let's get started. So to recap what we learned in time domain signal processing so far, so we learned about time shifting and scaling, amplitude shifting and scaling, modulation, correlation, convolution and zero crossing detection. So we also studied peak detection. So today we are going to study about envelope detection and smoothing, with the pattern matching being the remaining topic. So what is a signal envelope? So envelope is typically a smooth curve that outlines the extreme values of the signal. Like if you see this figure, so this blue curve is the signal, while the curve, which is pretty smooth and it is obtained by the extremas or peaks of the signal and the troughs of the signal, these are called envelopes of the signal. So typically in amplitude modulated signals, so this envelope represents the amplitude of the message signal as it varies over time. So this red one is the upper envelope formed by the maximas of the signal, whereas the green one depicted by the smooth curve combining the minimas of the signal is our lower envelope. So we have understood what is an envelope. Let us try to understand what is the problem of envelope detection. So given a discrete time sequence which is depicted by this blue lines, the task of envelope detection is to find the two envelopes E max n and E min n, which correspond to the upper and lower envelopes respectively. Like in this figure, if you see, so this is depicted by this red curve and the green curve. Now why should we do envelope detection? So there are a lot of applications. I would like to discuss three of them. One is demodulation in communication systems. As I already said that the envelope is typically a representation of the message signal in amplitude modulated signals. So if we want to do demodulation, and the envelope detection is a very good use case. In speech and audio processing, this envelope can give a lot of information about the speech signal respect to the pitch of the signal or some prosodic features of the speech. In biomedical signals also, envelope detection plays a vital role in many applications, like removal of the baseline drift or baseline wander in biomedical signals like ECG. Here you can see the example. So now let us try to understand what are the algorithms for envelope detection. So the three of the most popular algorithms include rectification with smoothing, peak detection with smoothing and Hilbert transform. So in this lecture, I would like to discuss about the first two topics, which are rectification and peak detection, and also since both of these methods use smoothing, so we will discuss the smoothing techniques as well. So first algorithm is rectification and smoothing. So in this, what is rectification? So rectification, typically you might have studied in terms of conversion of AC to DC. So in this context, rectification typically means taking the absolute value of the signal. So the first step of the algorithm is to take the absolute value of the signal x of n and then perform the low pass filtering operation on this absolute value signal. and you keep on doing this until you find a suitable Emax or your upper envelope. Now, what about the lower envelope? So, this is also done in a similar way, but not the same way. That is, first you get the inverted signal, that is minus x of n. Take the modulus and find the negative of that value, and that signal, let us say this is y n of n. So, perform low pass filtering on this signal y n of n, and this will give you the lower envelope. So, since this is an algorithm, we will understand or analyze the computation complexity of this algorithm. So, the first is taking absolute value. So, if the signal is of length n, so you have to take absolute value for each, which is typically an O of n operation. And for filtering, consider that we are using a convolution where m is the filter size. So, in this case, your O n dot m will be the operation of the filtering operation, and similarly the remaining two are exactly kind of same operations. So, it will be also O of n plus O of n dot m. Now, out of these two, the costliest operation is the low pass filtering operation. So, we can conclude that the complexity is order of n dot m. So, here are two examples of signals where rectification is performed, which will be followed by smoothing. So, if you see, this blue is the original signal and the red will give you the inverted signal. So, the upper half will denote the upper envelope. It is not the upper envelope. So, a low pass version of this positive signal will be the upper envelope. So, if you perform a low pass filter, it will be something like a smoother version like this. So, this gives you the upper envelope of this signal, whereas this will give you the lower envelope. Now, if the signal is a bit more complicated, so this is a beautiful sine like wave, but if the signal is complex, not complex in the sense complex values, but complicated in nature, so still you can use this method. So, you do this rectification first, and then on these values you can perform a smoothing operation to get the upper envelope, and similarly you can get the lower envelope. So, this technique is very nice when performing operations like demodulation, but in complex problems it may not be so straightforward. So, the second method often solves this, because envelope by definition is the interpolation of the peaks, and we already have learned lot of peak detection algorithms. So, let us apply peak detection first, and then we will interpolate the peaks. So, this is the second algorithm, which is peak detection and smoothing. So, in this algorithm, what we will do is, we will identify the local maxima in the signal instead of rectification, and the same will follow for the lower envelope as well. I am just talking about the upper envelope. So, this can be just simply extended for the lower envelope. Then we have to identify the peaks. So, identification of peaks, we have already discussed the various algorithms, and typically all of them or most of them have O of n complexity. So, first step is peak detection. The second step is interpolating between the peaks or the local maxima. So, how do we interpolate? We can generate a smooth curve, and we can use either linear or quadratic or cubic spline interpolation to interpolate the peaks, and that will typically have O of p complexity for p peaks, and typically this p is less than n only, not equals to. So, the next step or the last step is the smoothing operation, and in this smoothing operation we will try to reduce some presence of noise in the signal in the envelope, and typically again if we consider smoothing by using convolution operation, so this will be O of n dot n. Now, if we compare the complexities, so this smoothing operation is the most time taking operation. So, the complexity of this algorithm will also be O of n dot m. So, this is a typical example where we have a signal which is represented by this blue curve, and using this first we find the local maxima and minima. So, the red dots are the peaks which are the local maxima, whereas the green dots are the local minima, and then the interpolation is done, and this interpolation is pretty smooth. So, there is no need of any low pass filtering operation, but you can see that this is the method of finding the envelopes and it works well. Now, if the filter structure was a bit complex, then the low pass filtering will make the envelope smoother. So, now we have talked about the term smoothing, and this smoothing also appears as a time domain signal processing problem. So, let us try to learn some smoothing algorithms as well. Now, typically in the normal signal systems or signal processing course, this low pass filtering is termed as smoothing, but smoothing is not just a linear filtering operation. Smoothing can be non-linearly done as well. So, here we will study three popular linear filters. Linear means these have a kernel and you have to convolve these filters to find the smoothed version of the signal. Then order statistic filters, which are typically nonlinear filters, and they rely on order statistics like ascending order or descending order of the signal or window of the signal. And then another popular filter which is Savitzky-Golay filter. Now, those who are very familiar with Python based signal processing, they will see or they will use lot of Savitzky-Golay filter in their smoothing operations. So, let us understand these things. So, moving average filter, as the name suggests, so we take the average and then that central value of the signal is replaced by its averaged value. So, typically if I have a kernel, so say I have some signal value, say I want to do an average for a window of length 3, say L equals to 3. So, in this case my formula will be 1 by 3 summation k equals to 0 to 2 x of n minus k. So, typically if I put this, so y n is nothing but 1 by 3 and it gives me x of n plus x of n minus 1 and x of n minus 2. Now, this is a causal moving average filter. Why causal? Because it is the output here is not depending on any future value of my input, but in some implementations which are not real time, they can use non-causal implementations also, where instead of taking x n minus 2, they take x n plus 1. And typically if you see, this is the kernel 1 by 3 1 comma 1 comma 1. So, which is doing the average of the past 3 values of the signal. And now, since if the length of the signal is L and it is a convolution operation and the convolution is done in the naive way, so we will say the order is n dot L. Another important filter is the exponential moving average filter, and this is typically implemented in a recursive manner, or it is also an IIR structure where my output is dependent on some fraction of the present input and some fraction 1 minus that of the just immediate past output, and this alpha will determine that what fraction of my present input is to be taken and the previous output, which is of course dependent on the previous inputs as well. And since this is implemented in a recursive manner, so this is kind of a dynamic programming structure, and your exponential moving average filter will have a complexity of O of n. So, another similar filter is the Gaussian low pass filter. So, what is the difference with Gaussian and moving average is that when I take the average, I am giving each sample an equal weight, which is 1 by L, where L is the length of the filter. But in Gaussian, as you know, the bell shaped curve, so it has the highest weight to that central pixel, and as it goes away from the central pixel, the weight is decreasing, which means that it will give the highest weight to the present input, and as I go away from the present input, the weights will decay exponentially, like this bell curve. So, this is a typical Gaussian filter where you can take some value of sigmas, and that will give you your specific h of n. So, these are some comparisons. Say I have a noisy signal like this. So, with our moving average filter of size 5, with our exponentially moving average filter with an alpha value of 0.7 and a Gaussian filter of size 5 and sigma 0.2, you can see that the smoothing operations is varying significantly. So, here in moving average, we can see that it is smoothing it very nicely. So, if this is an envelope detection problem, then we can see that the moving average is performing nice because it is creating an envelope like structure. But on the other hand, it is removing some detailed information in this region, where the Gaussian on the other hand is retaining that. The exponential moving average is also retaining that, but my moving average filter is distorting or smoothing out that detail, which may not be desirable in many signal processing application, but for the context of envelope detection, this is preferable or may be desirable. Now, coming to a nonlinear filter, which is the order statistic filter. So, in this order statistic filter, so here it is very useful when we are dealing with outliers or impulse noise, and the three main filters in this context are the median filter, max filter and the min filter, and the complexity will be O of log of L and n log n. Why? Because there is a sorting operation required. Now, for example, say if I have some values like 3, 2, 7, 6, 5, and this value needs to be replaced. So, first I need to sort them out. So, it will be 2, 3, 5, 6, 7, and now if I am using median, so this middle value will be replaced by 5, which is the median. If I use a max filter, it will be 7, which is the same value, so it will have no effect, and if I use a min filter, it will take 2, which is the minimum of the window. So, these are the comparison, and technically we see that the median is doing well. So, it is retaining the structure kind of to a great extent, but the min and max filters are not in this case performing very nicely, but maybe again for envelope detection problem, this min and max filters may be useful. Now, coming to the last filter, which is the Savitzky-Golay filter. So, in this what we do is a polynomial fitting. So, we have some data points and a low degree polynomial is fit on the data points, typically of a small window, and the polynomial fit can be a quadratic or a cubic spline, and then a least square fit is made to the polynomial, so that the points in that window will be replaced by the least square fit, and this will typically smooth the signal, and this window needs to be moved from one place to another like a sliding window. So, this is the typical algorithm of Savitzky-Golay filter, where first you have to select the window size and then the polynomial order, like typically an order 2 or 3 is sufficient for most signals, and then we have to fit the polynomial. So, once this polynomial is fit, now the central value of the window is replaced by the window's polynomial. And one more important thing is that since we have to pick the central value of the window is typically an odd sized window, even for the order statistics filter also. And then we have to slide the window and repeat the same. So, thank you so much. We will meet again in the next lecture.